Hi there, AP Calc students. Now we're going to learn about another kind of differentiation, this called implicit differentiation. And up to this point, I think we probably mentioned this in class, we have found derivatives when they have been solved for y or solved for f of x. And so then when we find our dy over dx, it's a fairly straightforward task, albeit we do have lots of different formulas to keep track of. But in implicit differentiation, this is when we try to do derivatives when our function is not solved for y or f of x. And we'll see some examples here in this video. Now the trickiest part about this, I think, is this. Whenever we encounter a y variable, we do have to treat it like the chain rule, and we'll do this with our first little example that we have here. So dy over dx for this expression, y squared equals x. Now you might say, well, couldn't you solve that for y? We could, but we want to show you how this is going to work. So if we just find the derivative of this, now normally our derivative when we have a power would simply be this, right? 2y to the first, and it is in this case as well. But again, if we treat this y as something in parentheses like we did with the chain rule, we would now say that our derivative is 2y to the first, but then treating the y value as the parentheses, we don't know exactly what y is. We would also tack on this dy over dx, the derivative of y with respect to x. And of course, when we go over here to x, what's the derivative of x? It's just going to be 1, as we've seen before. Now, solving this for dy over dx, we would just simply divide both sides by 2y, and so my answer then would end up to be 1 over 2y. Kind of weird, and the weird part I think is especially this right here. So keep in mind, whenever you see a y from now on and we do this implicit differentiation, treat it like the chain rule. So 2y to the first, but then we have to tack on that dy over dx. I think that'll become more apparent as we do some more examples of this. That was my cat Puma jumping down from the table. Alright, here's our steps for implicit differentiation. Good to write these down. This is pretty standard fare for most of these types of differentiation problems. Number 1, differentiate both sides of the equation with respect to x. We just did that in our previous little example. Number 2, collect the terms with dy over dx on one side of the equation. So in other words, it's possible we might get more than one of these terms that has a dy over dx. We want to get all those on the same side. Then we'll factor out this dy over dx, and finally solve for this. And we'll see how that works, certainly in some examples on this video and also in class in the next couple of days. Alright, here's a first example, and as you might guess, we're looking for some slope type problem here. So we have a circle, x squared plus y squared equals 9, and the point -2. Actually, I think I meant to make this positive square root of 5. Both points are on the graph of that circle, which we would do. Alright, first of all, we'll try to do this algebraically, then we'll verify our answer by looking at the graph. So again, slope, whenever we see that, that means we're going to try to find the derivative. So here we go. So the derivative of x squared is simply 2x. The derivative of y squared is 2y times dy over dx. Saw that on our very first example. And the derivative of 9 is 0. Now, as our rule said, we want to try to get this dy over dx by itself. So the first thing I'll do then is subtract 2x from each side, like this. And then my last step is to do something with that 2y. So then my answer is going to be dy over dx equals -2x over 2y. 2's will cancel out, and we will end up with -x over y. What is that? That is the derivative, so that is the slope of that circle at that particular point. Now we could be a little bit more specific here. Let me change colors here a bit. So that means that at that point my slope is going to be the opposite of negative 2 over square root of 5, like this. So basically, that's going to be 2 over the square root of 5. And for the benefit of our next slide, if I figure out what that is as a decimal, that's 0.8944 approximately. Okay, so at that particular point, there's my slope. And now I just need to, for instance, come up with an equation. I guess my problem didn't initially call for that, but let's go ahead and do that. So here's my point slope equation. Y minus y1 equals m times x minus x1. We've used that a number of times already. Here's my specific x and y value, x1 and y1 there. And of course, here's my slope right here as well. So when I plug all these things in, I'm going to get y minus the square root of 5. Remember, we do want this to be a positive square root of 5. Now I put my slope in, which is 2 over the square root of 5, like that. And then I have x minus negative 2, which we know will turn into x plus 2. And so then, another step here just to unclog things a bit. 2 over the square root of 5, and then x plus 2, like that. So then I'm going to go up here where I have a little bit more room. So now if I solve this for y, as I usually would do, I would get y equals 2 over the square root of 5 times x plus 4 over the square root of 5. That's distributing my slope there. And then I'm going to end up with also plus square root of 5 when I solve that for y. Now I could figure out what the decimal is for this, and so my final answer, which has some decimals in it, is going to be 0.8944x plus, and here's when I combine my last constants there, I get a number like this, 4.0249. Now what that's going to be then is the equation of the whole line that is tangent to my point up here. Now, just to verify that, you've written down what that equation is. Let's go to our next slide where we have used the graphing calculator and see what we came up with. So sure enough, here's the circle. Keep in mind when you enter the equation of a circle on your graphing calculator, you have to solve it for y. And so 9 minus x squared, then you have to take the square root of that. Remember that the square root of this is not equal to 3 minus x. You cannot take the square root of just those individual parts when they are added or subtracted. And I do have to put in both the positive and negative of that, otherwise I'll only get either the top half or the bottom half of the circle. So here's my graph. Doesn't really look much like a circle because of the pixels of the graphing calculator, but it is the equation of a circle. Here's my point right here, the negative 2 point. And when I use the calculate menu of my graphing calculator and just look for the derivative, there's that number I got. And of course we remember looking back at our last slide that sure enough that was the slope at that point that I did get by doing this implicit differentiation. And my last slide is then putting in that actual equation that we figured out, and sure enough we can see that it is indeed tangent at that particular point and worked out well. Alright, last example here. This is just another practice with this dy over dx, and so let's take a look and see what this one has in store for us. So finding the derivative of that, of x cubed, of course, would just be 3x squared. That's a pretty old hat for us by now. The derivative of 5, since it's a constant, will of course be 0. And oh, looky here, what do we have? This is x times y, so we better go ahead and use our good friend the product rule. The product rule says the derivative of that is the first times the derivative of the second. Now, the derivative of y, we don't know exactly what y is, so we just write it as dy over dx plus the second, which is just y, times the derivative of the first, and the derivative of x or 1x is just 1. Puma, settle down now. Okay, so what we really have then is 3x squared and equaling x dy over dx plus y. Again, we want to try to solve this for dy over dx. So what I'm going to do first of all is subtract this y from each side like that. And then I still have that x over here, x times dy over dx. And I think you see that to solve this for dy over dx, Puma, you're creating a bit of a distraction here. These students are trying to listen, and you're shuffling papers about. So I have 3x squared minus y, and I'm going to have to divide by x. So there's my derivative right there. Pretty weird stuff. Again, we could find actual slopes at a certain point because now we have the derivative of that whole function. Implicit differentiation, kind of weird stuff, but I think you guys will catch on to it pretty good. Thanks for listening, and we'll see you in class.